Hi everyone, and welcome to Lecture 27 on antiderivatives. We've really reached the last part of this course. Instead of thinking about derivatives now, we're going to think about derivatives in reverse. And we're going to ask questions like, how do I go backwards from a given function? So I'll show you what I mean. So let's get a definition on the board here for what an antiderivative is. So here's our definition. We have a function, and we're going to call it capital F of x when I'm talking about the antiderivative. So a function, capital F of x, is an antiderivative of some function, f of x, on an interval I, if the following thing is true. If you take the derivative of capital F, and you end up getting little f for all x in the interval I. So we're trying to figure out what function did I have to have, so when I take its derivative, I get back to this original function here. And that's the game you play with antiderivatives. So let's do an example. We're going to find an antiderivative of f of x equals 2x. So that's our goal, is to find an antiderivative of f of x equals 2x. So we're looking for capital F here. So what's something I could use? Well, we need a function capital F of x. So the derivative of it with respect to x is equal to 2x. And what could I choose? Well, there's actually more than one option. Let's just consider capital F of x equal to x squared plus 5. Then what happens if you take its derivative? If you take the derivative, you get 2x plus 0. So this right here, this 2x matches our original function. So this is an antiderivative. However, like I said, it's not a unique choice, because I could have just said this. I said, how about, what if f of x was equal to x squared plus 100? Then capital F prime of x is also equal to 2x. So notice it says we want an antiderivative. It's not the antiderivative, it's just one of them. So there's many choices I could have chosen here to pick, so that the derivative of capital F is equal to 2x. All right, so this leads us to the idea for a theorem here. So we have a theorem. I'm going to switch colors again. So the theorem says, let capital F1 of x and capital F2 of x be antiderivatives of f of x, so some function, on an interval I. Then f1 of x, capital F1 of x, equals capital F2 of x plus c for some constant capital C. So this can be any real number here, so for us in this class. So what this is saying is that these two things may be different, but they're only going to be different by some kind of constant here. So here I have 5, here I have 100. So that's that theorem. Let's look at this theorem with some examples. So here I have lowercase f is going to be cosine. The question I'm asking is, what function do you have to take its derivative to get cosine? I'm going backwards here. And the answer to that is sine. If you know your rules very well, you'll be able to know them backwards as well. So the antiderivative of cosine is sine, but I could have also put any constant here that I wanted to, maybe like 5 or 100. So we just put a plus c here to represent that constant when we're going backwards. And this, we just call this the general antiderivative. So you're going to need to remember to put that plus c when you're dealing with antiderivatives, and it's just the general one. All right, let's go through some more examples here. So how about if lowercase f is equal to e to the x? Well, the derivative of e to the x is e to the x, so the antiderivative of e to the x is also e to the x. So to go backwards, we just do e to the x. But remember, we just have that plus c there as well. What about if I introduced a constant up there in the power? Then what is the antiderivative? Well, think. I need the function so that when I take the derivative, I'm going to get back to where I started again, which is f of x here. So what I'm going to need actually is 1/3 e to the 3x. And you can always check your work, too, for these problems. So if I were to check my work, that means I'm going to take the derivative of my answer. 1/3 is a constant. We have e to the 3x times, and then 3 for the chain rule. And notice these 3's will cancel out, and I'll get e to the 3x. And that's correct. That's what I started with here. The only thing I did not include, and hopefully I don't do that too much, I caught myself this time, is I need the plus c here, because it could have been any constant as well for the antiderivative. So this is the general antiderivative right here. All right, moving on. Let's look at this power function. So if you started with x squared, how would I go backwards? Well, you would need to take this power and go up 1. So you would add 1. We're so used to going forward and dropping this and subtracting 1, but to go backwards would be to add 1. And then we need something here so that when we take the derivative, it'll cancel, and we'll be back to where we started. You can check that that's 1/3. OK? So taking the derivative of this really does get you back to here. And this, I need the plus c. I almost forgot again. This is the plus c right here. This leads us to a fairly general rule. So if you have x to the n, and n is not equal to -1, so I'm going to make that specification, and n is not equal to -1, then this rule can be generalized. So what you do to find the antiderivative for this is you add 1 to the power, and then you divide by that new power. And that's how you're always going to do that. So here I started with 2. I increased it to 3, and I divided by the 3. So that's the general way of saying this. So you can think of this as a power rule, just backwards. All right, moving on. How about this one? So my original function is going to be 1/x. What function have we learned that when you take its derivative, you get 1/x? Well, this one was the natural log of x. So the antiderivative of this, the general one, will be natural log of the absolute value of x plus c. OK? Do I have any more examples? Well, I have a more involved one now. So let's say f of x is equal to 1 minus x cubed plus 5x to the 5th minus 3x to the 7th. And I'm looking for the antiderivative. So find the general antiderivative. Those are my directions. So let's go one at a time. Just like with derivatives, you can split up the derivative term by term. You can do the same thing when we're taking the antiderivative. So I'll focus on one at a time. What function did I have to differentiate to get 1? Well, that's x. And here is my power rule backwards. Increase the power to a 4 and divide by 4. This one, increase the power to a 6, divide by 6, but I also have that 5 that was just sitting there. And then finally, increase the power to an 8, divide by 8, and then I still have that 3 that's just sitting there. And then I could have had any other constant, so that when I take the derivative of this, I would get back to where I started again. So that's using the backwards power rule, I suppose, 4 times. Let's do one more. So here my example is f of x equals 4 root x minus secant x tangent x. I'm going to rewrite this. I generally always rewrite these things. So if you have a radical x, that's x to the 1/2 minus secant x tangent x. And now let's go ahead and do the general antiderivative. So if I'm going backwards here, it's a fractional power, but I still just add 1 to go backwards. So this is x to the 3/2. You're going to divide by 3/2. That's the new power. And then you have that 4 sitting there. That doesn't look too great, but we'll fix it in a moment. What function has secant tangent for the derivative? You have to know these very well to be able to do this. So the function that has secant tangent as its derivative is secant x. and then plus c for the constant. I really don't want to leave it like this. So I'm going to flip this up here, and I'm going to get 8 over 3. If I flip up and multiply, x to the 3/2 minus secant x, and then plus c. So this will be my general antiderivative. And remember, you can always take the derivative of your answer to check and make sure you get the original. So if you took the derivative of this, you should get back to where you started again, and you do. All right, I'm going to continue with a few more examples, and I'm also going to reintroduce position, velocity, and acceleration as well. So I'll see you in just a moment. Let's continue with a few more examples. So in this example, we have the second derivative is given as 1 plus x to the 4/5. And we're asked to find f of x, the original function. So the difference with this one is if we take one antiderivative, we'll be back to f prime. And we have to take a second one to get all the way back to f of x. So let's do that. So for f prime of x, I'm going to take one antiderivative. So the antiderivative of 1 is x. Differentiating that would get us the 1. Going backwards from here, if I add 1 to the power, I'm going to add 5 over 5 here. So this is going to be 9 over 5. And then I'm going to divide by the new power, but that's the same thing as flipping it. So please allow me to just do that. OK, so this is my general antiderivative once I've included the c there. If you're unsure, you could take the derivative of that, and you can get back to f double prime. But it looks like I'm good, so I'm going to continue. So now we just do another one. So for f of x, I take this, and I do another antiderivative. So here, increase the power 1, divide by the new power. Increase the power by 1, and then I'm going to have 5 over 9 divide by the new power, which is 14 over 5. I'm missing my plus sign here, so sorry about that. Plus, the antiderivative of a constant is going to be cx. If you took the derivative of this, you would just get c. So that's why I need to put x here. And then I have another constant. I'll just call it capital D that I could have had here, so that when I take the derivative of this, I would get back to this. All right, let's just clean up this a little bit. So I have 1/2 x squared. Here I have, if I flip this fraction up here, I'm going to have 25 over 126 x to the 14/5. And then this is plus cx plus d. And this is my general antiderivative. So it's the same process that we were doing. We just took one more antiderivative. That's all. All right, so given an initial condition, we can calculate the antiderivative of some function f. So I'll just say of maybe f of x. So before we weren't given an initial condition, so we had to put this plus c off to the side, because it could have been any family of functions here. But now, if I have an initial condition, it forces the function to be, the antiderivative to be one unique thing. So let's look at an example of that. My example is going to be f prime of x is the square root of x times 6 plus 5x. And I'm given an initial condition. So this is another thing given in the problem. I know that the original at 1, so f of 1 is 10. And we're going to find f of x. So this right here, where they told you the original function at 1 is 10, this is called an initial condition. This is initial condition. So they would give you this in the problem statement. OK, so first thing I'm going to do, like usual, I'm going to rewrite this as x to the 1/2. And I'm also going to go ahead and distribute it in. So I'm going to get 6x to the 1/2 plus 5. Here the power is 1. I'm going to add it to 1/2, and I'll get x to the 3/2. So this is my f prime of x. I've just rewritten it. Now let's do the antiderivative. So this means f of x is, increase the power by 1, I get x to the 3 halves, and then you get 6 divided by the new power, which is 3 over 2, plus x, increase this power by 1, so that's 5 halves now. 5 divided by new power is 5 halves, plus some c. We don't know what constant's there, but we're going to use this right here to find out. So let me simplify just a little more. 6 divided by 3 over 2 is going to get me 4. Here I just did keep, change, flip, so it would be 12 over 3. This one, 5 divided by 5 halves, is just going to give me 2. X to the 5 halves plus c. So that's just me rewriting the coefficients a little nicer. Let's use the initial condition now. So it says f of 1, that's equal to 10. That's what it says over here. But also, f of 1 is if you plug 1 into the function. So if I plug in 1 into the function I have 4 times 1 plus 2 times 1 plus c. So this means that 10 is supposed to be equal to 6 plus c. That means c has to be 4. So now we're forced to choose a particular constant here. And then the answer, the final answer, I'll write it over here, is all you're going to do is write what you had before. So this 4x to the 3 halves, this 2x to the 5 halves. And now we get to fill in what c is. So that's going to be 4. And this is the antiderivative. We get to actually pick the unique function that does this now with this initial condition. So this is my answer right here. OK. Let me write 2 things for you. The antiderivative of velocity is, and what do you think it is? The derivative of velocity is acceleration. The antiderivative of velocity is position. Remember, just think about this as going backwards. And then the antiderivative of acceleration, so if you go backwards 1, that's a velocity. OK, so we're going to use this, and we're going to do a few example problems. So here's my example. A particle moves with velocity v of t equals 1.5 square root of t. Also, we're given the initial condition that s of 4, the position of 4, is 10. Find the position function. And I'm going to label it s of t as usual. All right, so we know the antiderivative of velocity is position, so that's what I'm going to use. I'm also going to go over here and do my usual. This is 1.5 t to the 1/2 power. I'm just going to get rid of that root right now. S of t is, we need to do the antiderivative of this. So increase the power by 1. That's 3 to the 3 halves. That's hard to say. T to the 3 halves, sorry. What would the new power be? I would get 1.5 divided by 1.5. So actually, it's just 1 here. You can check my work. Plus some constant of integration c. So then here, I'm going to plug in my initial condition. So s of 4 equals, this is going to be 4 to the 3 halves power plus c. And this is supposed to be equal to 10. That's what it told us. So let's take care of this. If I do the square root of 4, that's 2, and then cube it is 8. So I get 8 plus c is 10. That means c has to be 2. And now that I have this, I can write the position function, which is going to be t to the 3 halves. And I get to plug in my c now. I go back and I plug it in, so plus 2. All right, and let's do one more example. So for this one, we're going to be given that the acceleration is cosine of t plus sine of t. We're given an initial condition for the position. At time 0, it's 0. and we're given another initial condition that the velocity at 0 is 5. And the directions are the same for this. We're going to find s of t, the position function. So notice we're starting with acceleration. So we start at acceleration, we do the antiderivative to get velocity, then we have to do another one to get the position, just like we did over here with this example where I had the second derivative and I had to go back twice. So that's the same idea here. So that's why I showed you this earlier, to show you that we can do it with this as well. So let's get velocity first. So we're starting with acceleration. We'll go backwards one to get velocity. The integral, oh my gosh, I said integral. I meant antiderivative. Sorry. Who said that? What's that word? I don't know. The antiderivative of cosine of t is sine t. And then the antiderivative of cosine is negative cosine t plus some c. However, if you weren't sure of that, you take the derivative and check your answer. So derivative of sine is cosine. Derivative of negative cosine is positive sine, because you get that negative sign here. Let's use the initial condition. So velocity at 0 is sine of 0 minus cosine of 0 plus c, and that's supposed to be equal to 5. That's what they told us here. Well, this tells us, this is 0, you get negative 1 plus c equals 5, and this lets us know that c was supposed to be 6. Let's take that and plug it in to the velocity. So we know the velocity should be sine of t minus cosine of t plus the 6 we just found. That's great, because now we can take this and do the next step. So the position function is just one more antiderivative from here. So the antiderivative of sine is negative cosine t. The antiderivative of negative cosine here, this is going to be minus sine of t. And then antiderivative of 6 is 6t. I just add that variable on there. And then the derivative of 6t is just 6 plus, I won't use the same letter. I'm going to use d this time for the constant of integration. So again, take this, check your work. Derivative of cosine is negative sine. That gets me back here. Derivative of sine is cosine. So I'm here, good here. Derivative of 6t, I checked that. Let's use our final initial condition. So s of 0 is going to be negative cosine of 0 minus sine of 0 plus 6 times 0 plus the constant d. And that's supposed to be, when you plug in 0 to the position, it's supposed to be 0. That's the initial condition. What does this mess give us? Here you have a minus 1. This is 0. This is 0. And this is d equals 0. So the only way for this to happen is if you have d equals 1. So this is our other constant that we get. And let's go ahead and plug that in for the final answer. So you have this negative cosine of t minus sine of t plus 6t. And the only thing I'm doing from here now is I'm replacing d with 1. And then given those two initial conditions we had from the start, we know that this was the original position function right here. All right, you should be more than prepared to do your lecture quiz. And as always, please reach out to me if you have any questions at all. Until next time, I'll see you. Bye.